Hi everyone, this is Mrs. Trigno and this is the graph translation theorem, which is lesson 3.2 in Algebra 2A. Now, if you have made it to Algebra 2A, I assure you, you already know what's going on in this lesson. This is all content that you're familiar with. You maybe haven't seen it written as a formalized theorem, and so that's kind of our focus for today is just what does this theorem actually say. But I promise you, you have seen this type of thing before, all right? This is going to look familiar to you. So first of all, throw back to geometry. Let's remind ourselves what a translation is. A translation is a movement where we're sliding something around, okay? And because we're just picking it up and sliding it, our graph is going to remain congruent to the original. We're not changing the size or the shape of the graph. We're just moving it to a new location under a translation. We have an algebraic way or an algebraic notation that we use for translations called a rule. And so with a rule, what we do is we take a coordinate xy and we show how it's mapped to a new coordinate. And so for translations, that's always going to look something like this. X plus h, y plus k. And already I'm hoping you're recognizing those letters. Okay, we've used those letters just recently in some of the other content that we've talked about. So I think by now we're all pretty solid on the fact that x is going to affect the horizontal translation and y is going to affect the vertical translation. Okay, because x goes left and right, y goes up and down on the graph. We should also point out that when that h value is positive, we're going to be moving to the right. And when the h value is negative, we're going to be moving to the left. And that should make sense to you because that's how it works on a graph, right? Positive values go to the right, negative values go to the left. When we're talking vertical, the positive k values are going to be moving up, and the negative k values will be moving down. Again, that's because that's how a graph works. Positive y values move up, negative y values go down. Okay? So if I look at this first example, it says under the translation, the image of 0, 0 is 7, 8. So we have taken the 0 and turned it into a 7, and this other 0 has turned into an 8. So the rule for the translation is going to look something like this. And I guess I should have put this back here. Usually we put a T here to represent that this is a translation. Right now we're only talking about translations, but just so you know why I'm doing this. So I'm going to say TXY maps to, and then we have to think about how did this point change? Well, we took the x value, right, and we added 7 to it, and then we took the y value and added 8 to it. That's how we got from 0 to 7 and 0 to 8. Now, if I had given you harder numbers here, and I use that term loosely, but if I had given you different numbers here, you may have had to actually figure out, you know, how much did we add or subtract from each one of these coordinates. But because they were zeros, this actually worked out really easily. So find the image of this point under this translation. So if I applied the translation to this coordinate, where would this particular point end up? Well, it tells me that my x value is going to get added by 7. So I'm going to say 6 plus 7 is 13. And then it tells me my y value is going to get increased by 8. Whoops, jumping ahead of myself there. Negative 10 plus 8 would give me negative 2. And so then my new coordinate would just be 13, negative 2. So all I did there was add 7 to the x and add 8 to the y. So now let's describe the movement. And let's go back up here to our rule that we wrote. If I'm taking all of the x's and adding 7, that's going to move me 7 spaces to the right. And then adding 8 to the y's is going to move me 8 spaces up. So I would say slide 7 right, and 8 up. So that's the movement that would describe how I would get 0, 0 to this coordinate here, and how I would get 6, negative 10 to this coordinate here. I would move it 7 to the right and 8 up. So now let's write down this theorem here. And this theorem has to do with how do we write equations for things? So we know we can write equations for functions, right? We can write an equation for a parabola, let's say. How do we write an equation to reflect a translation that's occurring? So if you need to, pause the video to write that down. I'm not sure if I left that in your notes or not, so you may have to copy it. but feel free to pause if you need to. What I want you to notice here is in my rule, which we talked about above, we have x plus h, y plus k. Notice that while I have a plus h in my rule, it's telling me to put a minus h in my equation. And a plus k in my rule becomes a minus k in my equation. Okay? You've seen this before when we've talked about like the vertex of a parabola, that when we look in the equation, the numbers all are backwards from what they really are. This has to do with a kind of a compensating. It's making up for the fact that we took our x value and slid it over by a certain amount, and we had to almost like translate it back to its original position to be able to calculate the correct y value to go along with it. So I'll do a demonstration of that in class sometime, maybe when we're going over homework together as a group, so that you can see what I mean by that. But just know that anytime you're working in an equation, and that's kind of the big key word here, anytime you're working in an equation, everything's going to look backwards. And you're going to hear me say that a lot in the next couple of lessons. So in this next example, I'm looking at an absolute value function. It gives me a rule here, and I want to apply this rule to this equation here. So with the x, my rule says I'm supposed to do x plus 4. When I put it in the equation, I'm going to put it in as an x minus 4. And anything you're putting with the x needs to be attached directly to the x, meaning in this case, I need to put the minus 4 inside the absolute value bracket. So it's going to look like this. Okay. And then I see y minus 7. So over here with my y, I'm going to write this as y plus 7. Okay. Now, what I'd like us to do now is describe the movement. So we're going to look at the rule to describe the movement. And then I want to look at it on a graph. I want to actually graph this thing and make sure that it did what it was supposed to, because you're kind of just believing me when I say that we're supposed to put a minus instead of a plus. Okay, I haven't proven it to you yet. So let's think about what this would do. This rule, and by the way, when you're trying to describe the movement, I would always refer back to the rule. The rule is what's telling you what's actually happening. The equation is always backwards, all right? So I wouldn't try to refer to the equation, I would refer to the rule. And in this rule, I have x plus 4, so that's going to move me 4 to the right. And then I have y minus 7, which is going to move me 7 down. Okay, so here's what I'm going to do. I'm going to open up a Desmos tab here. So taking a look at our functions here, the original function was y equals the absolute value of x. And on Desmos, you type that in as ABS. We can talk about how to put that on your calculator when I see you in class again. So absolute value of x, that's what my function looks like. It looks like a V. And what I want to see is if I put in my equation that we just came up with, which was y plus 7 equals the absolute value of x minus 4, is it going to move 4 to the right and 7 down? So let's type that in. Y plus 7 equals the absolute value of x minus 4. And if you look at even just the vertex of the two graphs, so the red one down to the blue one, we did in fact move 4 to the right and 7 down. So even though in the equation we put a minus 4, you'll notice that graph moved 4 to the right. And we put a plus 7, but it actually moves 7 down. That's because when you're writing the equation, everything goes in backwards from what it was in the rule. And again, there's some mathematical reasoning behind that. I don't know how important it is that you totally grasp why that's happening at this stage of the game, but I will try to show it to you when we go over homework in class. Okay? All right, so we're picking up here with example 3. Example 3 says the graph of y equals x squared is translated 2 up and 3 to the left. Write an equation for the image. It is always easiest to start with the rule. So I'm going to take this information here and use it to write myself a translation rule. So as far as my x goes, I want to make sure, because this is trying to trick me, right? It put it in the opposite order from what it usually does. The left and right is always your x, and the up and down is always your y. So 3 units to the left in my rule would be x minus 3. 2 units up in my rule would be y plus 2. Remember, the rule is exactly how it should be, okay? Minus 3 goes to the left, plus 2 goes up. When I write the equation, I'm going to put in an x plus 3 and a y minus 2 into the equation of y equals x squared. And remember, whatever's happening to the x needs to happen before the squaring gets applied. So the way that we indicate that in math is with parentheses. So instead of x squared, I'm going to write x plus 3 squared. And again, you'll notice that's opposite from what it was here. And then over here where the y is, I'm going to write this as y minus 2. Okay, so this would be your equation. This up here is the rule that represents the translation. I do want to point out one thing real quick, because you're going to see me do this probably on the answer key for the homework. There's a lot of times in algebra when we like to have y by itself for lots of different reasons. And so this is what's supposed to be happening. We are supposed to be putting a minus 2 over here with y. But sometimes you'll see that 2 moved over to the right side of the equation. And so then your equation would look like this. X plus 3 squared plus 2. So if you see a number hanging out down on the end here that's not being applied to the x, and I know it's not being applied to the x because it's not inside the parentheses, we have to first think about the fact that this really belongs to the y, and think about what would it look like if we moved it back over to the y side. And we're going to see that down in this next example, but I thought this was a good place to point it out, that I could take this 2 and move it to the other side. I don't care how you write your answers. I don't care if you leave it over here with the y or if you move it to the other side, as long as the sign is correct, regardless of where you put it. Okay, so to get to the point where we can sketch a graph of this thing, I need to think about a lot of different things. I need to first of all think about what parent function this is related to, but we'll come to that in a minute. I need to think about what translation is occurring here. And probably to think about the translation, I should start by writing a rule, okay? So my rule, I'm going backwards now. So now I have the equation, but I have to remember that the equation is backwards land. So when I see x plus 3 in the equation, I know that it's actually an x minus 3 going on up here in the rule. Now, this over here, this plus 2, just like I was talking about in this last example, this actually belongs to the y. And I know that because it doesn't belong to the x. It would be in the parentheses with the x if it did. So I need to think about the fact that if this plus 2 were over with the y, it would really look like a minus 2, right? And then in my rule, that really becomes a y plus 2. So it's almost like I switched it and then switched it back. And I know that feels weird. If you want, you could get to the point where you just know that if the number's over here on the right, that it does match what's going on in the rule because it got flipped when it moved to the other side. But this is my rule, which means that whatever graph I'm looking at, this translated to the left by 3 and up 2. Okay, so now we have to think about what this graph should even be. What shape of a graph are we looking at? Notice I'm doing all of this without typing it into a calculator. To think about the parent function, I'm going to pretend these numbers don't exist. So the 3, I'm going to kind of like mentally block out. And the 2, I've already got that scribbled out. And look at what you're left with. You're left with y equals 1 over x squared. Okay, this is where those parent functions that you learned in the last lesson are going to come in handy. So I know that the graph of y equals 1 over x squared looks like this. It looks like a hyperbola, but it's side by side with asymptotes at the x and y axis. Okay, that's y equals 1 over x squared. I want to take this graph and move it to the left 3 and up 2. When your graphs have asymptotes, I find it easiest to think about it as moving where the asymptotes are located. So if I move to the left 3, nope, sorry, left. I know my right and left, I promise. Okay, so here's to the left 3, and up 2 would be here. And so I want to think about it like this is now my new horizontal asymptote, and this is my new vertical asymptote. And now using those pink lines as a guide, I can draw my new function. So I can draw along here, and I can draw along here. Now, maybe you didn't need to draw the parent function to begin with. I did so that we could remind ourselves what the shape looked like. The question was really just asking for what's here in pink. I don't mind when you're doing these problems if you draw the parent function also, as long as you make it crystal clear to me which one is supposed to be the image, which one is supposed to be the new picture. I don't care if you use a different color or a highlighter, or if you even just draw a note and say, hey, this is my actual answer. But if you're going to put both things on the graph, just make sure I can tell the difference between the two. Okay, I think that's enough to get you started on the homework assignment for 3-2, looking at translations. Again, just to remind you, anything that's in the equation, which is where you have like the y equals, is going to be backwards from what's really going on. That's going to be a very common theme in this chapter, and it's one that you're familiar with already. Okay, thanks a lot. I hope you guys have a great day.